Okay, guys, we are back. It's 12:54 now. I still can't sleep. But this is a scary proof. Let's be honest here. This is theorem 5.17. I'm gonna just copy it over and then I'll read it out. But first I want to get to my scratch paper to feel safe. So I don't I'm introducing these proofs as kind of getting more familiar. Whoa, it's big again. With Sorry, I don't know why I'm surprised each time. Getting more familiar with the cyclic notation. I had Ada rigorously define that in one of our sessions, and she was quite peeved with me. I'll phrase it like that, of why I would do such a thing. But it's kind of weird. I mean, we're doing a lot of stuff here, right? This a to the n, and it's an integer, and what does contains mean? That's the weirdest part of this proof for me. I think it should be pretty standard, and by standard, when I originally proved this and on my little flashcards, I did not use what Webson loves to call the corollary. I don't think I'm spelling that right at all, but I've seen this called the one-step subgroup test. So we're going to use that today. And by today, I mean this morning because it's currently almost 1 a.m. One-step subgroup test. What does that mean? Well, we're going to show that for A and B and H, that A, B inverse is in H. And if that is true, then H is a subgroup of G. Sorry for my sloppy handwriting. I can feel it getting worse as I become more and more past my. I've never not slept, so surely I'll fall asleep soon. This is new territory. I've only been up this late like once in my life, but I can't sleep. So what we're gonna do is let's take what do we want to call them? Let's take two elements in H. I normally like to call those like H1 and H2, but because the whole point is that the elements in H are of the form of A to some power, we're just going to call them that for now, and then label them as A to the R and A to the S. We can do this because we're going to specify, I don't like how I'm using commas so much. Called A to the R and A to the S, where R and S are like and they are integers. Oh, that's a crappy. That's better. So now these definitely are in H because they're A to some power where the power is an integer. Really standard. Um, because we know, let's start a new sentence. We know that um, a to the negative s is the is the inverse of a to the s, because, and I'm being very like extra here, being pedantic. A lot of this doesn't need justification, but I always I find that it's more like you learn more if you're being like this. But anyway, we know that a to the negative s is the inverse of a to the s because a to the s times a to the negative s equals a to the 0 equals e. Um, and as like a final point, a to the negative s is in H because negative s is in the integers. So remember, we're not dealing, luckily, thank goodness, this would make the proof way, I think it make the proof impossible. We're dealing with just the integers, not like the positive integers. So we know there's a negative, and we know that it's the inverse of a to the s. So finally, let's just put it all together. A to the R times a to the negative s. This is mirroring our A B inverse, right? that's just going to equal a to the r minus s, thanks to the power, the exponent rules. And r minus s, integers are closed, is also in the integer. And so it's true that a to the r minus s is in H. Thus, H is a subgroup. We've done it. We've shown that H is a subgroup of G. This, I consider it to be the easy part. Once we like understand subgroup tests and we understand cyclicness, the part that always confused me is and is the smallest subgroup of G that contains A. That is, every subgroup containing A contains H. And I went, whoa, what does that mean? Honestly, it's still a little iffy, which is why making these videos I consider just to be or to be just as beneficial for me as for you. So let's just kind of start feeling out. Secondly, we will show H is the smallest. Ooh, I'm getting lazy. Smallest. I think this is my third video that I'm uh, recording as of tonight. Oh, it's 1 a.m. That's fun. Uh, Containing A. How do we do that? I'm very tempted to go over to my flashcard and look at how I did this, but the whole point of trying to learn is you try it without the flashcard, and then you look and you go, okay, that's what we do, or that's what the textbook says I should do, or what Webson said we should do. Oh, this is testing my memory. I'm sorry, I'm trying to think rapidly as I stall. Um, how do we show? Oh, okay, I'm vaguely remembering things. If so, if we look at the wording here. Once again, we're going to kind of look at the theorem to give us guidance. That is, every subgroup containing A contains H. Okay, so let's start there. If a subgroup, I'm not going to name this subgroup, just a subgroup of G contains A, which is that special element that generates G as defined in the theorem and as cyclicness is defined, um, then we know something about this subgroup. It has to contain A to the N, which is really, it's like, oh, why is that true? Well, um, I'm going to write that out, contains A to the N. And now for the justification. Because a to the n is just a multiplied by itself n times. A to the n is equal to a times a times a dot 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 times a. And then I suck at drawing this little thing, but n times, there's going to be n a's. And so because A of n is equivalent to that, and because subgroups are closed, which is to say that, no matter how many times like if I multiply an element by another element in a group, that will be in. That's the definition. And so I'm just multiplying A by itself a bunch of times. That's definitely going to stay in the subgroup because it's closed. And so because of that, um, uh, let's go back up to up here. We defined H as being A to the N for some integer n. Thus, containing, sorry, it's getting really sloppy. Containing A to the N is the same as containing H. Oh, wow, that's not even spelling the word right. Containing H. So, since every subgroup with A contains H, H must be the smallest containing A. I'm getting really sloppy. Oh wow, that's not even the right letter. So this part I find a little confusing. It feels like a leap that maybe isn't justified. But what we're saying is since H contains A, and it like basically is just A, right? It's just A to the n, all the powers of n, right? For any integer. And because if any subgroup contains A, it also contains H. H has to be like the fundamental basic one and must be smaller than all the rest because there's nothing that we saw that had A but didn't have H. And so we can't, ooh, sorry, we can conclude that H is the smallest subgroup containing A. And we are done.